Hey everybody, thanks for the invite to give a talk at the Nearly Carbon Neutral Topology Seminar. I'm going to tell you about some 3 and 4-dimensional invariants of satellite knots computed via knot Floer homology. My name is Holt Bodish, and I'm here from the University of Oregon. So the plan for the talk is I'll give a little bit of background on knot theory and knot Floer homology, and then some of the sort of history of computations in this field. And then I'll give some results in the second talk, where I'll talk a little bit about immersed curves and the bordered pairing theorem, and plus some concrete results in terms of a family of patterns. So computations for families of satellites. All right, so let's start at the bottom with what is a knot. So a knot is an embedding of the circle S1 into the 3-sphere, considered up to ambient isotopy, and a lot of the time we draw knots by their planar projections or diagrams in R2. We draw a broken line strand to indicate an undercrossing. So that tells me how that knot actually embeds in S3, even though I'm just drawing it on the plane. These first 2 knots, the trefoil knot and the figure 8 knot, are the first 2 knots you'll encounter in a knot table. They're the only 3 and 4 crossing knots. And these other knots are sort of auxiliary knots related to those 2 through a construction that I'll tell you about later in this talk. But something I want to mention first is what are the quantities we're after? And these quantities involve this fact that any knot bounds an embedded orientable surface in the 3-sphere. We call such a surface a Seifert surface. One way to construct it is from a knot diagram. So if I have a knot diagram like such, I can resolve these crossings by skipping the crossing along the orientation of the knot. And then I have 2 disks left over. And those 2 disks are attached by these twisted bands. So if I color one of those disks yellow and the other one I color green, that's how I can build a surface whose boundary is the knot K. Okay. So this algorithm works for any knot diagram to construct an orientable embedded surface with boundary K. And I am interested in computing the minimal such genus of any Seifert surface for any diagram K. Okay. So one reason that you might like the 3 genus is that it detects the unknot. So the unknot is the only knot that bounds a disk in S3. All right. A related quantity is just what would happen if I pushed that surface a little bit into the 4-ball, which the 3-sphere sits as the boundary of. And I might want to know what the minimal genus of properly embedded surface in the 4-ball, whose boundary is the knot K in S3, would be, how that's related to the 3 genus. So just a remark, the 4 genus of K equals 0 is equivalent to K being slice. That is to say, it bounds a disk in the 4-ball. And there are many knots that are non-trivial that bound disks in the 4-ball. So these two quantities are different, and so studying both of them can lead you to some interesting conclusions about knots. All right. The last question I want to ask is, when is the knot complement S3 minus a neighborhood of K, where a neighborhood of K is just a thickened up version of the circle, so it's a solid torus. embedded inside of S3, a locally trivial fiber bundle over the circle. That is to say, when is S3 minus the neighborhood of K realized as the mapping torus of some homeomorphism phi from sigma to sigma that we call the monodromy of that fibered knot. In that case, we say the knot is fibered. So I want to study these three sort of 3- and 4-dimensional invariants of my knot. And I want to study them under a construction. So I want to study what happens to them when I take a satellite knot. So a satellite knot is the knot I get by having as input a knot in S3 that I call the companion, and a knot in the solid torus that I call the pattern. And it outputs a knot that I'll call P of K inside of S3. How do I do that? Well, again, I can think about thickening up the knot, removing it from S3, and I'm left with, I have a 3-manifold with torus boundary, and there's a torus-shaped hole where that neighborhood used to be. I can fill that torus-shaped hole with this solid torus S1 times D2, carrying along the pattern as it sits inside of there. For example, here I have this pattern in purple. If I glue that solid torus so that the curve I just drew, L, maps to the curve lambda in red. Lambda is sigma, the Seifert surface, intersect with boundary of a neighborhood of K. I get S3 back, and I get this knot on the right, where I just have drawn sort of 2 parallel copies of the knot and connected them by a little twist, as shown here. Okay. One other thing I want to mention is that to a pattern, I can associate an integer called the winding number of that pattern, which is the algebraic intersection of the pattern with the meridional disk. Okay, that quantity shows up in the following formula, which is how does the 3 genus of a satellite knot relate to the 3 genus of a pattern and the 3 genus of the companion? So in 1953, Schubert argued that, well, the 3 genus of the satellite is the winding number of the pattern in absolute value times the genus of the knot K, plus this quantity, which is called the genus of the pattern. So this is the minimal genus of a relative Seifert surface, sigma tilde in S1 times D2, where the boundary of sigma tilde is the pattern together with winding number of P copies of the longitude. Okay. So this formula might seem really great, but it kind of begs the question, what is the minimal genus of a relative Seifert surface? Similarly, you can determine when is the satellite knot fibered. P of K is fibered if and only if K is fibered in S3 and P is fibered in S1 times D2. So we're still, even though this is a great equivalence and it tells us when the satellite knot fibers, we still have to figure out a way of understanding when is a pattern fibered in the solid torus. Similarly here, to compute the 3 genus, we have to figure out what is this minimal genus of a relative Seifert surface. I'll mention that these other 2 quantities, the 4 genus of satellites and the monodromy of fibered satellites, I don't know anything general to say about them. There's a lot of, I'll just mention about the 4 genus, there's a lot of open questions about the 4 genus of satellite knots. For example, is the 4 genus of the positively twisted Whitehead double of the negative trefoil knot 0 or 1? We'll see the positively clasped Whitehead double pattern later, but I just wanted to mention this and say we just don't know. We don't really have, in the same way as we have a formula for the 3 genus, a formula for the 4 genus of these satellite knots. And we'll see later that we can sort of fix up some properties about the monodromy for certain satellite knots with certain companions, but we can't do it in general. Awesome. So one other upshot of these formulas, even though these quantities G of P and P fibered in S1 times D2 are still semi-mysterious, a consequence of these two results is that the genus of the pattern is the genus of the pattern applied to the 2,3 torus knot, for example, minus the winding number of the pattern. So there's a genus of T23 here, but that's just equal to 1. And 2 is that, P is fibered in the solid torus if and only if P of T23 is fibered. So I just picked my favorite small fibered knot, and I said, well, I can apply these two theorems to that as a companion. It's going to allow me to greatly simplify the computations I need to do to figure out the genus of the pattern and whether or not the pattern is fibered. I just have to test it on this one case where the companion knot is the trefoil. Awesome. So how do I do this? Well, one of the tools that I like to use is knot Floer homology. So I'm going to tell you about knot Floer homology and why it's helpful for answering this question, or these questions. So knot Floer homology, sort of in its simplest form, is just a bi-graded abelian group. A little bit more sophisticated form, it comes to you as the homology of the associated graded of a filtered chain complex. And that filtered chain complex is called CFK hat of S3 comma K. And this is sort of defined in terms of a Hagar diagram for the pair S3 comma K. Okay. And from that, I can associate a Z-filtered, free, finitely generated chain complex, graded chain complex over the field with two elements. So it's got this integer filtration here. And if I look at the associated graded and I take the homology, that's going to be the piece of knot Floer homology in that grading A. Okay. So for some terminology, this grading, the A grading is called the Alexander grading, and the M grading is called the Maslov grading. Okay, so the knot Floer homology in Alexander grading A is the homology of this particular piece, this quotient of the filtration of the complex CFK hat. So basically, by construction, by definition, you see that there's a spectral sequence from this filtered chain complex to something, and the something that it ends up being is HF hat of S3, which you can see is just the field with two elements. It's one-dimensional. Okay. And from that spectral sequence, I can get an integer, which is tau of K, and that will be the minimal Alexander grading of a generator surviving this spectral sequence. So that's the quick rundown on knot Floer homology. Let me tell you what it's used for. I guess let me first show you these examples. So here is the knot Floer homology of the trefoil knot. Each dot represents a generator at that Alexander grading. Here, this is a dot at Alexander grading 0, 1, and Alexander grading -1. The knot Floer homology is one-dimensional in each Alexander grading where it's non-zero, and you can see this canceling differential that sort of is the spectral sequence from CFK hat to, well, HF hat of S3. And you can see also that tau of this knot is 1 because the Alexander grading of the blue dot is 1, which is the one that survives the spectral sequence. Similarly, over here, we have the same, we have a similar decomposition into Alexander grading. So this time there's 3 generators in Alexander grading 0. And there are these 2 canceling differentials. The Alexander grading of the surviving generator is 0, but it still is non-zero in just 3 adjacent Alexander gradings. It's not surprising, given the following result, that the 3 genus of my knot K is the maximum Alexander grading where the knot Floer homology is non-zero. And you might know that the trefoil and the figure 8 knot are both genus 1 knots. So that tells us that they should both be non-zero, only in Alexander grading 1, 0, and -1. Another amazing property of the knot Floer homology is that if you know the rank of the knot Floer homology in topmost Alexander grading, you know whether or not the knot is fibered. So it's fibered if and only if that dimension is 1. The genus detection is due to Ajvath and Szabo, who are the originators, along with Rasmussen, of the knot Floer homology. And fiberedness detection is due to Ni and Juhas. Also from about 2004, Ajvath and Szabo proved that this integer tau gives a slice genus bound. That is to say, the absolute value of it is less than or equal to the slice genus, or the 4 genus of my knot K. And pretty recently, in 2020, Ni showed that actually the next to top piece of the knot Floer homology in Alexander grading G-1 tells me something about the monodromy of the fibration if my knot is fibered. So if I have a fibered knot and the dimension in the next to top Alexander grading is 1, then the monodromy of K is left or right veering, which I don't want to say too much about, but I'll just mention that it has something to do with how the monodromy acts on arcs in your surface. So if I have an arc there, for any arc relative homology class in my surface, if phi sends that arc to the right locally in some little neighborhood of that intersection with the boundary, then it's called right veering. So here's A, here's an arc, here's the image of A under that monodromy, and that needs to happen for every such arc. And I can tell that about the monodromy just by computing this next to top piece of the knot Floer homology. So somehow this tells me that, well, I was really interested in these topological quantities of my knots, the 3 genus, the 4 genus, the fiberedness, the properties of the monodromy if I knew the knot was fibered. Well, all of those are sort of encapsulated in the knot Floer homology if I know the groups together with their Alexander grading decomposition. So some prehistory on this. Around 2007, Matt Hedden studied Whitehead doubles, or more generally n-twisted Whitehead doubles of a knot K. So this is the pattern that I would get, that I would draw if I wanted to figure out to draw the satellite Whitehead plus of K. And you can see he shows that tau of the Whitehead double of K, well, it depends on the twisting parameter, which is just how many twists I add in here. And it depends on the tau of the companion knot. So if the twisting parameter is bigger than or equal to 2 tau, it's 0. If it's less than 2 tau, tau is 1. And then there's a couple results along these lines. I'll mention a few, one of them from Adam Levine, which computes tau of the n-twisted measure pattern of an arbitrary knot in terms not only of tau of the companion knot, but also this quantity epsilon of the companion knot. Similarly, Jen Hom computes tau of the PQ cable of any knot, where this PQ cable, you use the PQ torus knot as a pattern. Here I'm using the 3-1 torus knot as an example. And again, that depends on tau of K and it depends on epsilon of K. So that's an example of people determining the knot Floer homology of a family of satellite knots together with the Alexander decomposition, because in order to know tau, you have to know the spectral sequence, which is equivalent to knowing how sort of the Alexander grading decomposition, together with a little bit of extra information. All right, sort of a little bit closer to some of the low-dimensional topology that we were talking about in dimension 3, Pekova and Wang in 2021, they studied when is the n-twisted measure pattern fibered. And using this result of Hirasawa, Murasugi, and Silver, they showed that the n-twisted measure pattern of a knot k is fibered if and only if k is fibered and n is not equal to -1 or 0. Okay. And more recently, or sort of around the same time, Wenzhou Chen computes tau of the zero-twisted satellite with companion either T23 or T-23 for a family of patterns that have the property that if I apply them to the unknot as the companion, they are isotopic to the unknot. So these maybe I would call unknotted patterns. And they're not any old unknotted patterns. They're 1-1 patterns. So that is to say, they admit these kinds of particularly nice kinds of Hagar diagrams called 1-1, called genus 1 doubly pointed bordered Hagar diagrams. So we'll talk about genus 1 doubly pointed bordered Hagar diagrams in the next talk, as well as so the general principle here, which is to compute HFK hat of a satellite knot, we need to use the bordered pairing theorem. Which says that, well, maybe I'll state it in terms of CFK hat. This chain complex is chain homotopy equivalent to something. And here I'll just write it down and I'll discuss it a little bit more in detail in the next lecture. So it's this sort of derived tensor product of these two invariants, CFA hat and CFD hat. CFD hat is just associated to the knot complement and CFA hat is just associated to the pattern. So you can kind of divide and conquer, and that's how all of these results are proven, and it's how the results that I'll show you in the next video are going to be proven as well. Thanks for watching.